Hello, this is our introduction to the Euclidean algorithm. In this video, we're going to learn the definition of the greatest common divisor of two integers, or GCD for short. And I want you to become comfortable computing the GCD by hand, just by factoring. Then we're going to learn how to compute the GCD using the Euclidean algorithm. This is a classic algorithm, like the classic algorithm. And one of the things is just amazingly fast. So if you didn't know this, one of the things that's keeping all of our credit cards and personal information safe on the internet is cryptography. And the mathematics underlying cryptography is number theory. And in particular, the fact that it is actually very hard to factor large numbers. Okay, so that difficulty of factoring is what's keeping all of our personal information safe. And the Euclidean, the problem of computing the greatest common divisor of two integers sounds like it's a problem of involving factoring when you first hear about it. And in fact, if you did this when you were in elementary school, my kids are in elementary school and junior high, they have done some of this and they always learn to factor. And that's right, because it's the intuitive, and I think it helps you understand what's going on, way to do it. But the Euclidean algorithm is so much more efficient. And what we'll see is we don't actually have to know the factors of two numbers in order to find their GCD, which is kind of mind-blowing. Okay, so we're going to notice some things in the Euclidean algorithm that in our first step, the GCD of A and B is going to be the same as the GCD of B and R, as we'll see, and that we're going to see that using the Euclidean algorithm to compute the GCD of large numbers doesn't necessarily mean the steps get too large. Okay, that's why it's so great. All right, so let's look at a couple definitions. First, there's the definition of greatest common divisor. So if I have two integers, their GCD is the largest integer that divides both A and B. More formally, an integer C is the GCD if C divides A and C divides B. So that's the part that's saying C is a common divisor, or it divides both numbers. And the other part is that if D divides A and D divides B, then D is less than or equal to C. And what that mouthful is saying is that any other divisor, maybe D, that's a common divisor, has to be smaller than C. So C is larger than all the other common divisors. Okay, there are lots of other ways to state the Euclidean algorithm in a way that makes sense to people and is perfectly comprehensible. But stating it this way with those two steps is, I think, the best way to state it if you're going to be writing proofs involving the Euclidean algorithm, and we will, okay? Because it gives you two things to check, and in particular, two opportunities to use the definition of divisibility, right? And so when you use that definition, it's in the proof poem, right? It's giving you an opportunity to write down something you know, and that thing you know, because it's a definition with an equation in it, right? It will give you some equations that you can then do some computations that will put you in the next part of the proof poem that then you can interpret and sort of put in the logical framework of the proof. Okay, so this definition with its two parts, it might not be the easiest to understand or to remember when you first learn it, but it's really important to use this format because it will be helpful in proofs. All right, so of course the first thing we do when we see a new definition is some examples. So these are some warm-ups, and if you want to, you can put me on pause and see if you can do the warm-ups by yourself. Okay, so I'm gonna do the warm-ups now, pause me anytime, and you can check your work after. All right, so let's compute the GCD of 8 and 4. Well, what you might notice is that 4 actually divides 8, and no number bigger than 4 can divide 4. So the GCD of 8 and 4 is 4, right? And this is something that's always going to happen when one of the numbers divides the other. That number will be the GCD, okay? So I'll say that 4, and I'm going to write here because 4 divides 8. All right, so now what's the GCD of 12 and 8? Here, one doesn't divide the other, so we have to do a little more work. It might be something that you can do in your head, but I want you to, so, our motto here is think deeply of simple things, to think, what are you doing when you're doing this in your head? Well, maybe, I think you're probably factoring the numbers in your head, right? And you're doing it quickly because they're small. So you could say, well, 12 is equal to 4 times 3, and 8 is equal to, well, 2 times 2 times 2, and in particular 4 times 2. And so we can see here, when we look at the factors, the greatest common divisor is going to be 4 again. Okay, so the GCD of 12 and 8 is equal to 4. All right, so I'm just getting my pen working. What's the GCD of 13 and 8? So you might remember that 13 doesn't have any other factors other than 1 in itself, right? No positive factors. So 13 is prime, and then the only number that's going to divide both 13 and 8 is 1. Okay. And these numbers were small, numbers that we're kind of familiar with. And I think whenever, as a general principle, you start with a new definition, the definition is new. So start with something comfortable. And then once make sure you understand it. And then what you want to do is kind of think, okay, what's a case that I would be maybe a little less sure about, right? Branch out from there. Also, look at the cases that you can do that you're comfortable with and ask, do I see patterns? What's going on? And see what you wonder about. All right, so this last one, 2016 and 1000, what's the GCD? You might say, 2016 is a big number. I don't know its factorization. Oh, that's going to be a long time. Yeah, okay. I luckily knew that, oops, and thought maybe it would be helpful to factor these beforehand. So I did factor them, and my notes tell me that 2016, I'm going to write this in the big space off to the side here on the other page. So 2016 happens to be the same as 63 times 32. Of course, you could factor the 63 and the 32 more. But you won't need to solve this problem. And 1000 is equal to 125 times 8. And when you look at this, you can see, well, the 63, that's a 7 times 9, and the 125 is just 5 times 5 times 5. So I think the greatest common factor here is going to be 8. Okay, so the GCD of 2016 and 1000 is equal to 8, right? And it's not that hard, but it probably did give you pause for a minute, right? And went, whoa, okay, that I'm gonna have to think about. Well, instead of factoring, we're gonna use the Euclidean algorithm, and we're gonna use the Euclidean algorithm on each of these 3 problems and see how it works, first of all, and then try to sort of like analyze the steps, even though there won't be too many steps to analyze. All right, so the Euclidean algorithm, we're going to assume that A and B are both natural numbers and A is greater than B, because if they're equal, then the GCD is just, they're numbered, but they are. Okay, so we're going to find the GCD using the Euclidean algorithm, we're going to use the division algorithm over and over and over again. Okay, so first we divide the bigger number by the smaller one. So that's the first step. of the Euclidean algorithm here. So we're writing A equals QB plus R, but because we know we might have to do this over and over and over again, we're going to have many quotients and many remainders. We're calling this Q1 and R1. That's our first quotient and our first remainder. Okay. And then, well, what if that first remainder is 0? That means B has to be the GCD, right? Just like when we computed the GCD of 4 and 8. So if the GCD is 0, we're done. If it's not, we're going to do the division algorithm again, and we're going to let B be the new A, and we're going to let R1 be the new B. And so that's what's going on in the second step of the Euclidean algorithm, right? And again, if that remainder is 0, then I claim we're done. Otherwise, we again shift the whatever was playing the role of B now plays the role of A, and our new remainder plays the old role of B. All right. So we call the first 0 remainder RK plus 1, and then RK is going to be the GCD of A and B, right? So let's just do this algorithm and a bunch of, in these 3 examples. And then afterwards, I want to go back and think about it a little bit, and that will set us up for proving the Euclidean algorithm in the next video. All right, so if I want to find the GCD of 12 and 8, the Euclidean algorithm says I use the division algorithm. So how many times does 8 go into 12? Just once. So that's 1 times 8 with a remainder of 4. Okay, so that remainder is not 0. So what I do is I say my old B was 8. My first remainder was 4. And I think, okay, so now I have to write the division algorithm here. And I do get a remainder of 0. And what that tells me then, this is R2. So, oops, I'm not going to write it like that. Let me not write it like that, where it looks like that is the whole expression is equal to R2. That is R2. R1 equals 4 equals the GCD of 12 and 8. Okay, very good. So now let's use the Euclidean algorithm to compute the GCD of 13 and 8. Similarly, we use the division algorithm. 8 goes in 1 time, this time with a remainder of 5. Again, that's not 0. So we let 8 play the role of A, and 5 is going to be what we divide by. Here, 5 goes into 8 1 time with a remainder of 3. All right, still not 0. So we're going to do this again. We have 5 divided by 3 goes in 1 time with a remainder of 2. Bear with me. Still not 0 remainder, got to do this again. 3 divided by 2 goes in 1 time with a remainder of 1. And then finally, I have 2 divided by my remainder of 1 with a remainder of 0. This is my first non-zero remainder. So the GCD is the number that comes before, and I see the GCD of 13 and 8 equals 1. But it took kind of a lot of steps. So in this particular situation, the numbers are so small that you may have been able to see that the GCD of 13 and 8 is equal to 1 just in your head. And this is more steps than you would need for something like this. So don't take heart, don't worry. This is a relatively long GCD for an example that I wanted to show you. I just wanted to show you one that had a bunch of steps, okay? And so we could do it. And then, okay, so now you've seen that and you might be kind of worried, like the GCD of 2016 and 1000, is that going to take more steps than that little example? Let's see. So when I do the Euclidean algorithm, I have to divide 2016 by 1000. So that's going to go in twice, right, with a remainder of 16. And okay, so 1000. Now I have to divide that by 16. And 16 goes into 1000 how many times? Let's see, I think it goes in a bunch. I'm gonna cheat and use a calculator here. 1000 divided by 16 is, I think, let's say it goes in 61 times. And then 61 times 16 is equal to 976. So I get a remainder of 4. Let's see. Did I do this right? Hold on. Oops, I see my mistake now. I just read my calculator wrong. So this should be a 62 here. So if you do 62 as the quotient, then your remainder ends up being 8, which is what I expect if my GCD is supposed to come out to 8, which we had already. So now I still don't have a 0 remainder, but I do have a non-zero remainder, which I secretly already know is the answer, right? So now I'm gonna look at 16 is my new A, and 8 is my new B, and I say, yay, it's actually a factor of 16, so I am done. Whew. So 0 is my first 0 remainder, or this is my first 0 remainder, and 8 is my last non-zero remainder. And we see that the GCD of 2016 and 1000 is equal to 8, and it involved very, very few steps, right? The numbers are big, but it was really only like a 2-step computation. Compare that with the example above, where the numbers were actually very small, and yet it took longer. So actually, it's kind of hard, and you should try this, okay? Try this now, to think up pairs of numbers where you try to compute the GCD and you get a lot of computations, right? One thing that happened with 2016 and 1000 is that they're actually both big, and so even though they were both big, in my first division algorithm step, the remainder got small right away, right? 16 is pretty small. So I have I have a way of making Euclidean algorithm computations as long as I want. It turns out that if you compute the GCD of consecutive Fibonacci numbers, and so we'll talk about Fibonacci numbers later in the course, then the computations grow at a predictable length, a predictable pace. And so 13 and 8 are consecutive Fibonacci numbers. And I chose that example purposefully so you could see something with a bunch of steps. All right, so we've noticed that using the GCD of large numbers doesn't necessarily mean that a computation gets long. And the other thing I want you to notice is that the GCD of A and B is the same as the GCD of B and R in each of these examples and in each step, right? So let's pay attention to like the second example, computing the GCD of 13 and 8. We know that the GCD of 13 and 8 is 1. And if you look at the GCD of 8 and 5, which is kind of what we're computing on the next line, oh, the GCD of 8 and 5 is still 1. And the GCD of 5 and 3 is still 1. Oh, and the same thing will happen in the other one. The GCD of 2016 and 1000 is 8. The GCD of 1016 is also 8. And what you can see actually is that, and this is key, the first step of computing the GCD of 13 and 8, for example, is this division algorithm line here, okay? This second line has two interpretations. It's the second step of computing the GCD of 13 and 8, but it's also the first step of computing the GCD of 8 and 5. And so if you've done some computer science, you might say, wait, this is kind of like, maybe it's like a recursive algorithm. So in the next video, I'll recast this for you as a recursive algorithm, and we will prove that this is correct based on some of the level 2 work that we're going to do in class. Okay, thanks.